So far we've been looking at single particle quantum mechanics, single electrons, single protons. Now we would like to extend our discussion to multi-particle systems, multipartite states as they are called. Suppose, and this is chapter 8 of Beck's book. We've gone up to chapter 15. We missed out this chapter 8 because I had kept this for later discussion. So let me motivate what are multi-particle states or multipartite states. And one of the real powers of quantum mechanics, they are manifest in these multi-particle states and operations. Suppose I have a crystal. It's a non-linear crystal. What this crystal does is that it takes one input, which is a single photon, perhaps. It's in a certain polarization state, a certain frequency, omega. Let's call this frequency omega p. This is the input frequency. There is a certain wave vector associated with this photon, and what I get at the output are two photons. So I input one photon, I get two photons out. Now, energy has to be conserved and momentum has to be conserved in this process. So these photons are generally called the signal and the idler photons, S and I. Okay. So if energy has to be conserved, this means that this omega S and this omega I must add to give omega P, because this is the principle of conservation of energy. The other process that must happen is that if the wave vector for the incoming photon is Kp, it must equal the sum of the wave vectors for the outgoing photons. This is the conservation of momentum. Alright. Both of these photons are created at the same point in time. So there is correlation between their energies and there is correlation between their wave vectors. That is, this is just the momentum of the photon, right? We know that the momentum of a photon E is just h bar E. So the momentums are correlated, the timing is correlated, the energies are correlated. Another thing that is correlated is the polarization state of the photons. So if this incoming photon, which belongs to what is called the pump beam, so this is the pump photon, this is the signal and this is the idler photon. So if the pump photon is in a particular polarization state, for example, the polarization is pointing out of the plane of the wavelet. Okay. Then these photons will have the same polarization state amongst themselves and they will be orthogonal to this polarization state. So if there is pointing out, this is in the plane of the wavelet. So if this is a horizontally polarized photon, both of these are vertically polarized photons. So now, if this is vertically polarized, both of these are horizontally polarized photons. So this is a non-linear optical process that happens in some crystals. For example, one of the most popular crystals is BBO, beta BBO. BBO is barium borate. The barium borate crystal, whose crystal plane has a certain orientation with respect to the incoming photon. This type of process is called down conversion. And what I have shown here is a type 1 down conversion. There are different types of down conversion processes. So in this type 1 down conversion process, there is an incoming pump photon, there are two outgoing photons, and the frequencies, the timings, the polarization states are all correlated. Now if we look at these photons, we have a two photon system. And if we just look at the polarization degree of freedom, we have a Hilbert space that is now spanned by 4 basis states, which means we have a 4-dimensional Hilbert space. If you just look at the incoming photon, we have two-dimensional Hilbert space because we just have one photon. Now we have two photons and we're looking at the polarization states. Remember, we're not looking at the direction of the photons or any other property. We're not looking at the timings of the photon. We're just looking at the polarization of the photon. So our concern is the polarization degree of freedom. So if you look at the polarization degree of freedom, we have two photons. Each photon lives in its own, each polarization lives in its own Hilbert space. So this photon has a polarization that lives in a two-dimensional space. This photon has a polarization that lives in a two-dimensional Hilbert space. Two-dimensional means you need two basis vectors to define its polarization state and two vectors to define its polarization state. However, if you look at this joint system, this is a joint system or a bipartite system. A bipartite system. You can have tripartite system, quad, tetrapartite system and so on. So in this bipartite system, we have a Hilbert space that is much bigger than the polarization state of just one photon. We have a four-dimensional Hilbert space. Okay? Each polarization of each photon lives in its own Hilbert space, but if you look at the system jointly, we have a bigger Hilbert space which is four-dimensional. Okay? And we can express the basis states in the following way. The basis states for the first photon are simply cat H, cat B. So this is one possible basis, okay, isn't it? So these vectors form a basis, an orthogonal basis for the first photon. For the second photon, we also have a similar basis. Now, these bases span a Hilbert space. This basis spans a Hilbert space. And if you join the two Hilbert spaces together, the process of joining is through this symbol, which is called a tensor product. Okay? If we conjoin the two Hilbert spaces together, we form a four-dimensional Hilbert space. And the basis states will be spanned by four basis vectors. And those basis vectors are represented in the following way. We can have H cross H. This is one basis vector. The other basis vector is H cross B. Then we can have B cross H. We can have B cross B. Right. So these four states form the basis of a four-dimensional Hilbert space. Okay. Now there are different ways of representing these states. One is putting a tensor product, the other is just dropping out the tensor product altogether. Just writing these states in this form. And assuming that the first position belongs to the first photon and the second position belongs to the second photon. For example, the first position could belong to the signal, the second could belong to the idler. Another possibility is to represent these states. Now these are just quantum states, these are states. We can represent these states as H, comma H, H, comma V, 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 comma H, and V, comma V. And keeping in mind that the first position belongs to the first photon, the signal, and the second belongs to the idler photon. Now, these four states span four-dimensional Hilbert space. For a two-dimensional Hilbert space, we can draw a block sphere. Okay. So this could be cat H, this could be cat B, this could be superposition, and so on. However, for a four-dimensional Hilbert space, we cannot draw such a block sphere. For a three-dimensional Hilbert space, we cannot draw a block sphere. Now, the difference is, so you can just assume that these basis vectors span a bigger dimensional Hilbert space. Okay. Now, let's look at how operations act in higher dimensional spaces for these multi-particle systems. For example, I have these two photons coming in. Okay. Now I perform a unitary operation on the photons. Okay. So this is my first photon, the second photon. This photon is in the state, say, psi 1. This photon is in the state psi 2. I have a two-dimensional, a four-dimensional space because I'm just looking at the polarization. Remember that this is a two-level quantum system, this is a two-level quantum system. I can also have this to be a two-level system, this to be a three-level system. Each of these could be a three-level system. Each of these could be a continuous system. So, in general, this is the general scheme of multi-particle quantum mechanics. Okay. Now, my input state that I'm preparing is a tensor product of psi 1 and psi 2, right? I can call this psi, keeping in mind that this is a four-dimensional vector. Now, if some unitary operation u1 acts on this state, okay, and some unitary operation u2 acts on this state, and the effect of u1 is solely on psi 1 and the effect of psi u2 solely on psi 2, then these are called local unitary operations. Okay. So how do I express these operations? The new state that I will achieve here. So I input the state psi here. Here I get a new state. I call that state phi. Now this phi is a four-dimensional vector. Now how do I express this phi? This phi is basically on the first qubit u1, on the first photon u1 is acting. It's a unitary operation. So I get u1 psi 1. On the second photon u2 is acting. Another unitary operation. Okay, so this is my new state. I can also express this. Now all of this is notation. I can also express this as I am inputting a state of psi 1 crossed with psi 2, and my unitary operation is u1 tensored with u2.
So u1 u2 का कोई पास ना हो?
ये बस unitary operation. ठीक है, कोई सी unitary operation. ठीक है. ये rotation operators हैं जो psi 1 और psi 2 पर act करेंगे. अच्छा. Now this is another way of writing the same expression. Assuming that the first operation in the tensor product acts on the first cat, the second acts on the second. And preserve the order. Okay. Alright. Now it's also possible that after this operation I have a gate or a unitary operation that is totally global. It acts on both the qubits together. Because this is a four-dimensional vector, there is no harm in having a 4x4 matrix that acts on this four-dimensional vector. Okay. Which is truly global. Okay. So the new state that I achieve here, suppose it's chi. Again a four-dimensional vector. Now this chi will be given by u3 acting on phi, or u3 acting on the state, u3 acting on u1 hat u2 hat, which acts on psi 1 cross psi 2. Okay. Remember, now all of this is notation, it's just getting familiar with the notation. If I have this unitary operation acting on the first photon only, then I can make this into a global gate. Okay? And this global gate would be represented as U1 crossed with the identity operation. Okay? I can write U1 as U1 crossed with the identity operation. So this U1 can be replaced by the U1 crossed with the identity operation, and this can also be written as a global gate, and this can be replaced by identity operation crossed with UT. Okay, because identity means that you're making the identity operation act on the first photon and U2 on the second.
प्रोडक्ट के हिसाब से हम U3 को अंदर ले जा सकते हैं
ये देखो U3 अंदर कहाँ इधर?
यस सर अंदर ले जा सकते हैं
नहीं ये एक 4 डायमेंशनल मैट्रिक्स है, ये 2 डायमेंशनल, ये 4 डायमेंशनल, इस पूरे को बाहर ही रखिए, अंदर ही लेके जा सकते हैं। If you have an operation like U1 crossed with identity plus identity crossed with U2, and this is a truly local operation. These are local transformations. U1 is acting on the first photon and nothing is happening to the second photon, and nothing is happening to the first photon, something is happening to the second photon. Okay. So these are truly local operations. If you need true global operation, you need to have something like this. Plus some U3 crossed with U4. Okay. So this where both of them are neither of them are equal to identity. So this is a true global operation that is mixing, that is creating correlations, as I have explained later. Remember that if I write a unitary operation in this form, then this is a 2 by 2 matrix. If I am talking about the polarizations here, this is also a 2 by 2 matrix. Okay, and this overall is a 4 by 4 matrix. If I am talking about the polarizations here, if I am talking about 2 qubits in other words. Okay, let's look at a few examples. Suppose I have this type 1 down conversion. Okay, so my input state is say cat H, cat H. Okay, this is my input state. Now what I would like to do now, I have these 2 photons, cat H, cat B. I perform a unitary operation on the first photon only. This is a half-wave plate that is at an angle of 45 degrees. So what this half-wave plate will do, it will convert this horizontal state to the vertical state. Okay. So at the end, what I will achieve is here I will get the vertical, and here nothing is going to happen. So I can write the rotation operator for this half-wave plate, tensor it with the identity, and I will achieve this state. Okay. So operations are, I've been talking about unitary operations, but operators can be general. They don't have to be unitary operations. They can be measurement operators, they can be any operator whatsoever. For example, there's plenty of examples in your book, so I will not go into them rather. This is quite simple stuff. Let's look at the calculation of inner products in these multi-particle systems. So I'm sticking to the example of type 1 down conversion, which means I have 2 photons. Okay, 2 photons created in some input state, cat H, cat H. So for these 2 photon states, I can form inner products in the 4-dimensional space. For example, if I have a state cat H, if I have this state, or which is also written as H tensor to H. Okay. It's a 4-dimensional vector. I would like to find the inner product with, say, V at 45 degrees. Which means that the first photon is in the vertically polarized state and the second is tilted at 45 degrees. So I can form this inner product. This inner product will be written in the following form: V, bra 45 degrees. Okay. Cat H tensor to H. Okay. Alright. Now the 2 Hilbert spaces are independent. What does this mean? This means that if I want to form this inner product, I will have to look at the projection in each Hilbert space independently. So this will open up, this inner product will open up in the following form. I have Ravi. This is connected to get H in the first Hilbert space. This is a scalar complex number, and 45 degrees, this dual vector is connected to H. Okay. So this inner product between this and this is formed in the first Hilbert space, and this inner product is formed in the second Hilbert space. I will get 0 because the inner product of B with H is 0.
So ये first वाला H1 है, दूसरा H2 है. Inner product जब हो गई. So बिल्कुल right hand है. ये जी इसमें H1 है फिर H2 है.
ये okay. So these I form this inner product like this, and I form this inner product in the second Hilbert space for the second photon like this. Now sometimes if you want to avoid confusion, you can put in a small 1 here and a small 2 here, a 1 here and a 2 here. Okay, so this is 1, 1, 2, 2. But I am avoiding these superscript to subscript because it just clutters the notation. Okay. So I can form inner products. I can also compute probabilities. Now, if we have a single particle quantum mechanics and I prepare the state chi, okay, I have an observable O. Alright, I get certain eigenvalues. If O is an observable and the eigenstates corresponding to this observable are represented by lambda n, for example. I get the eigenvalues lambda n, the eigenstates lambda n. Okay, O is an observable, these are the eigenvalues, these are real numbers corresponding to the measurement outcomes. Okay, so if my observable is O and I input a state psi, my observable is O, I am measuring O, this means, then the possible outcome is just the eigenvalues. And the probability that I will obtain lambda n as an outcome, given my input state is psi, is simply, what is this? This is simply the projection of psi onto the corresponding eigenstate modular squared. This is one of the postulates of constraint. Okay, so there are possible outcomes, lambda 1, lambda 2, all the way to lambda n. And if I would like to find out the probability with which I get a certain outcome, I just take the inner product of the input state with the corresponding eigenstate and modular square. Okay, quantum mechanics 1. Now I can also express this inner product modular square in the following form. This is simply psi lambda n psi, isn't it? Okay. Now this is, I can replace this outer product. This is an outer product. Okay, what can I replace this with? ये आउटर प्रोडक्ट है, ये एक ऑपरेटर है खुद. ठीक है, ये किस तरह का ऑपरेटर है? कैट लैम्डा एन ग्राफ लैम्डा एन. आइडेंटिटी तो नहीं, आइडेंटिटी तब हो जब आप सिग्मा लेंगे. प्रोजेक्शन ऑपरेटर, दिस इज जस्ट अ प्रोजेक्शन ऑपरेटर ऑन लैम्डा एन. ठीक है, ये definition याद है. Projection operator on some state phi is cat phi bra phi. Okay, the projection operator, it just projects onto a particular outcome state. Okay, this is is what happens in the normal measurement process. So the measurement, the probability of measurement is just the expectation value of the projection operator on the eigen state corresponding to the eigenvalue for which we are measuring the probabilities. Okay? So these probabilities are just the expectation value of the projection operator and the expectation value in the desired input state, and the projection on the eigenstate corresponding to the eigenvalues for which you would like to find out the measurement probabilities. बात समझ में? ठीक है, चलो मैं इसको आधा मिनट देता हूँ, थोड़ा सा इस पर गौर कर लें, तसव्वुर कर लें, बहुत सी मैंने लफ्ज़ कह दिए। Now let's look at an example. Suppose I prepare an input state for a two-particle system which is L 45 degrees. So the first photon is left circularly polarized and the second photon is polarized linearly at 45 degrees. Now I am interested in calculating the probability that my first photon is horizontally polarized and the second photon is vertically polarized. I would like to calculate this problem. Okay. So what I would do, I would like to form a projection operator in the four-dimensional Hilbert space. Okay. The projection operator that I will form is, in the first Hilbert space, the projection operator is ket H bra H. Okay. And in the second Hilbert space, it's ket E bra. But this is my projection operator. I can also express everything in matrix form. Remember that. I'll do that. Now, if I would like to find out this probability, this simply means that I would like to take this four-dimensional projection operator and calculate its expectation value in this input source. Okay? So the probability, the desired probability, will turn out to be H or H B, right? L 45 degrees, L 45 degrees. Okay? Now this operator will act on the first photon, this operator will act on the second photon. This bra will act on the first ket, this bra will act on the second. Remember this. So you have to preserve the ordering and you have to take into account which operator acts in which Hilbert space. Okay. So I don't want to do the calculation, this is something you do on your own. Okay. Everything can also be represented in some basis. For example, if I have chosen the basis such that ket H is being represented by 1, 0 and ket B is represented by 0, 1 in each of the two Hilbert space, two-dimensional Hilbert spaces, then my four basis states in the four-dimensional space can be written as tensor products of these two vectors. For example, if I would like to find the matrix representation of the quantum state ket H crossed with ket H, I just take the tensor product of these two vectors. Okay, now I am using a particular representation. Okay, I will represent the cats by the corresponding vectors. Okay. Now this is a representation that I have chosen. I need to define my representation in every case. So this tensor product is calculated, and how is it done mechanically? I take this first element and multiply it throughout by each of the elements of the second vector. So 1 multiplied by 1 0 is 1 0. This 0 is then multiplied by the element like this. Okay. Likewise, cat H crossed with cat B is 1 0 crossed with 0 1. This is 0 1 0 0.
So एक जिनमें जैसा एलेट 45 को लिखा
ठीक है, इसी तरह सारे चारों आ जाएंगे. If I have a state like L crossed with 45 degrees, I know that my L is 1 over under root 2 1 iota. Right? This is my left segment equals right. Crossed with 45 degrees, which is 1 over under root 2 1 1. So I can form this cross product or vector product. I will get half 1 1 iota iota. So in the basis defined by these four vectors, okay, this is the representation of this quantum state in the basis that is defined by the four vectors that are formed in the top two. Okay. Remember that this quantum state is really independent of a basis. I choose a different basis, it will be represented differently. Likewise, operators can also be written in the four-dimensional basis. Okay? For example, if I have an operator, let's write this operator, the projection operator, in the four-dimensional basis. So there are P, the projection operator that I have defined above, cat H, bra H, tensor J, cat P, bra B. Now the matrix representation of this product, it's a 2 by 2 matrix. Using the same representation that we defined above is 1 0 0 0, right? And this is 0 0 0 1. Okay, so I will get 1 0 0 0 1. This is what I will get. So which means that this 1 is multiplied by this matrix, I will get this block. When this 0 is being multiplied by this matrix, I get this block. When this 0 is being multiplied by the matrix, I get this block. And finally this 0 is being multiplied by the matrix, I get this block. So this is the representation of this particular projection operator in the four-dimensional space. Okay, I can do more complicated things as well. Suppose I have an operation, say some operator A. This operator A is given by sigma x into the identity operator. Now could you tell me if sigma x is a unitary operator? Is it a rotation? It is a rotation about the x-axis, about the y-axis through y, about the x-axis through y. It's a rotation. So this is a unitary operator, this is a unitary operator, this is also a unitary operator. Okay. Now this operation is physically, it means that we're doing a pi rotation on the first photon in its two-dimensional space and doing nothing for the second photon. Okay, this is do nothing for the second photon. And if you would like to represent this in matrix form, simply have 0 1 1 0, which is the representation of the Pauli X operator in the particular basis, in the Zeeman basis of the computation basis, where it is called with the identity operation 1 0 0 1. Identity just doing nothing. Okay, so I will get 0 0 0 0 0 1 1 0 0 1 1 0 0 0 0. So I will get a matrix which has one the cross diagonal. Okay. I can do more complicated things. I can do sigma x cross with sigma x cross with sigma y, and so on.
How did we get 0 1 1 0?
So identity over.
Also,
First time.
So I can form these operations in higher dimensional spaces as well.
So it is necessary for operators that both of them will have the same dimension.
If I have two particles, right? This is a two-level quantum system. Okay? Right. It is spanned by two basis vectors. This is a three-level quantum system. Okay? Was it? For example, this is a spin half particle, this is spin one particle. Okay? Then, what's the dimensionality of the Hilbert space? 6. ठीक है? So इसकी जो dimensionality अगर a है, इसकी dimensionality n है, the dimensionality of the Hilbert of the combined Hilbert space is kn. This is spanned by two basis vectors. This is spanned by three basis vectors. ठीक है? For example, if I am talking about spin, the basis vectors for this, they could be represented by 1 or alpha and beta, right? These are the basis vectors, okay, which are the eigenstates of the FZ operator. And for a spin one particle, I will have three basis vectors. I can represent them by 1, 2, and 3, right? These are the eigenstates of the FZ operator where spin is equal to 1 now. Okay. Now the 6 basis vectors will be alpha crossed with 1, alpha crossed with 2, alpha crossed with 3, beta crossed with 1, beta crossed with 2, beta crossed with 3. Okay. And I can also choose a representation. For example, I can represent this alpha by 1 0, I can choose this beta by 0 1, I can choose this 1 by 1 0 0, this 2 by 0 1 0, this 3 by 0 0 1, and I can then take the tensor products. I will get 6 plus 6 matrices for the operations. Okay? So it's not necessary that each one of them is a two-level system. We can have multi-particle quantum chemistry. We need to have these 2 different or 3 different or 4 different. Each one of it has its own dimensionality. Each system has its own dimensionality. Okay, now I would like to, with this background of general multi-particle quantum states, how do we represent them, we can form inner products, we can calculate probabilities. I would like to talk about one of the hallmarks of quantum mechanics, which makes quantum mechanics really different from classical mechanics. We are generally not covered in undergraduate courses, but it's extremely important. It's called entanglement. Okay? Entanglement वही है किसी कोर्स में, किस में मॉडल अच्छा. Suppose I have a crystal. talking about a different kind of down conversion, which is called type 2 down conversion. Okay. What happens in this type 2 down conversion is that I input a photon, the pumped photon, omega p, frequency omega p. I get 2 photons at the output. Frequencies omega s, omega I. Again, the momentum and the k vectors, the energies are conserved. They have to be conserved. This incoming photon is at 45 degrees. It's a 45 degrees polarized photon. It's a single photon state. I get a bipartite system at the end because I get 2 photons. Okay. Remember, this has to be a non-linear process. It's quite a complicated process. I'm not concerned with the atomic physics behind what's going on here. Okay. So I get 2 photons, and now it is impossible to actually to talk about single photon on its own. So this combined system of 2 photons has a particular quantum state. Okay. That quantum state is, suppose, ket H. If this were the quantum state, then it would be type 1 down conversion. If this were the quantum state, I could say that the first photon is horizontally polarized and the second photon is also horizontally polarized. Okay? If I got a state like this, ket P crossed with ket P, I could say that the first photon is vertically polarized. The second photon is also vertically polarized. And remember, I am taking single photons here. So I just input one photon, I get 2 photons, a pair of photons out. And these photons come out at the same time. They are correlated in time. The momentums are correlated, their energies are correlated. Correlated means there is a relationship. If this is perfect down conversion, 50-50 down conversion, then this omega s equals omega I. But if I have an output of this kind or an output of this kind, I can be sure about what the state of the photon is. This photon is, if this is my output state, this photon is horizontally polarized, and so is this. If this is my output state, this is vertically polarized, and so is this. Okay, and I input keep on make multiple copies of the incoming photon at the same polarization. I will get the same state again and again.
So इसका type 2 और type 1 में क्या difference है?
अभी मैं type 1 किया, ये type 1. अब type 2 में क्या होता है कि your output state is neither this and it's neither this. Rather, your output state is like this. Ket H plus ket B and this.
So in type 2 we only get those 2 alternatives.
No, in type 1 you get these alternatives.
Only these 2.
We can also get depending upon the incoming, the outputs are always orthogonal to the incoming, right? So in type 1, as we have here, if this is horizontally polarized, we get ket B. If this is vertically polarized, we get ket H. If this is 45 degrees, we will get minus 45, minus 45. Okay. So in type 2 down conversion,
So can you please raise
in type 2 down conversion, this is the output that we get. Now we have to explain this out. What does this mean? Okay. Now this is a quantum state. Lives in the 4-dimensional Hilbert space. It's a joint prescription for the 2 photons. Okay. Of course, this is a ket. This is a ket because it can be represented as a vector. Anything that can be represented as a vector is a ket. A ket is something that can be represented by a vector. Okay, so this is a new ket. Let's call this ket phi, and let's put a small plus on top of it. Phi plus. Okay. Now this kind of state is an example of what is called a Bell state. Okay. honor of John Bell, who talked about these states in his 1964 paper. Now, this quantum state is a four-dimensional state. Let's first represent this in a particular basis. In the basis that we've written here, okay? Let's call, I'll give this basis a special name. Let's call this the Zeeman basis, okay? हमने क्यों वन में भी इस basis को यही नाम दिया, ठीक है? और the computational basis. Now, in the Zeeman basis, this state is represented as 1 over under root 2, 1, 0, 0, 1. ठीक है ना? Can you confirm this? Cat H is 1, 0, 0. Cat B 0, 0, 0, 1. So you add them up to get this. So this is the cat for the output from a type 2 conversion process. Okay. Now the question is, what does this physically mean? G. What does this physically mean? So this is our state. If I just look at the first photon, and if I ask you the question, is it horizontally polarized or vertically polarized? What would be your answer? I'm not looking at the second photon. So what I'm doing here, I'm doing an experiment in which I get these two photons, okay, in this joint state. Okay, this is my signal photon, this is my idler. Now I put one of them in the dust bin, which means I don't look at it. ठीक है, मैं आंख में मूल लेता हूँ, बिल्कुल उसको ना इग्नोर कर देता हूँ, और मैं इसको एक सिस्टम में सुधारता हूँ जो कि PAHP है, right? Which is an analyzer along the HP direction. So I have two possible outputs. The two possible outputs are, I can either measure cat H or I can measure cat B. Correct? Now, what's the probability that this detector will fire? And what's the probability that this detector will fire? One over half. Half. But this can be half. ठीक है? होगा ये, इसको हम प्रूव भी करेंगे मैथमेटिक्स. कि if I'm not looking at the second photon, I'm just looking at the first photon, and I would like to analyze project this photon onto the horizontal vertical basis, which means I would like to pass it through this measurement device, which is PAHP. Okay, whose possible outcomes are cat H and cat B. Okay, this is by the way is implemented by the polarization operator. Okay, so I get an output cat H. My measurement outcome is +1. If I get this, if this detector fires, then it's -1. If this detector fires, एक मान से आपको याद होगी. तो अगर मैं ये इनपुट स्टेट लेता हूँ, यानी यहाँ पे इनपुट स्टेट मेरे पास phi है, ये बेल स्टेट है, and I'm ignoring the second photon. Just looking at the first photon, there's a 50% probability that this detector will fire and a 50% probability that this detector will fire. So it's totally random, perfectly random, like a pure coin toss, whether I will get the first photon is horizontally polarized, I can project it with 50% probability to the horizontal state and 50% probability to the vertical state. Okay? It's totally random. ठीक है, we'll prove this mathematically. Similarly, if I repeat this experiment such that I ignore the first photon, I put this into the dust, I trash it, and I look at the idler photon, pass it through a PAHB. This is my tie to down conversion crystal PBO. Then there are two possible outcomes for the second photon, cat A and cat B. Okay, there's 50% probability for this and 50% probability for this outcome. Now the really strange thing occurs. So what this is suggesting is that if I just look at one of the photons and I don't care about the second photon, I get my result is totally random. Okay. Alright. So this would also suggest that this photon is a mixture of horizontal and vertical. So if I would like to build up these probabilities, I will have to repeat the experiment multiple number of times. Okay, if I would really like to verify that these probabilities are 50%, so I will repeat the experiment multiple number of times. Okay, so one might argue that okay, you're repeating the experiment multiple number of times. What's happening here is that half of the times the photon here, so there are different possibilities. One possibility is that the signal photon is in the state 1 over under root 2 h plus v. Right? If I build up the probability that approach 50%, one might argue that the probabilities that the state of the photon that I prepared here is this state. है ना? ये पॉसिबिलिटी है ना? अच्छा, और मैं रिपीट करता हूँ एक्सपेरिमेंट, और अब इस दफा मैं फर्स्ट फोटोन को इग्नोर करता हूँ, सेकंड फोटोन को एनालाइज करता हूँ, and I get these 50% probabilities. So the same observation in the same experiment, one could argue that if the signal photon is in this state, the ideal photon is in this state. ठीक है, याद रखिए आप माइनस भी हो सकता, ठीक है. तो so one might argue that the quantum state here before I make an observation is just the tensor product of these states. कैसे कहा जा सकता है ना? तो the tensor, so the input, psi input, one might argue is the tensor product of these states, which is half h plus a, मैं सिर्फ प्लस साइन ले रहा हूँ, b plus b h plus b b. आ जा सकता है. यानी ये 1 over 2 मतलब 1 over root 4 है, ये नॉर्मलाइज है. अच्छा, अब ये one might argue that these outcomes are also reproduced by this state. ठीक है, but what we've argued is that this type 2 conversion gives this state. So this state gives the same measurement outcome as this state. Apparently it seems so, है ना? क्योंकि ये बिल्कुल रैंडम इवेंट्स हैं. तो this Bell state is giving the same measurement outcomes in experiments of this kind with this possibility. So this is possibility number 1. This is the second possibility. There could even be a third possibility, by the way. The third possibility is, अच्छा ये याद रखिए, ये एक कैट है ना, ये वेक्टर है, ये भी एक वेक्टर है, तो ये एक सुपरपोजिशन है. One might even argue, some conservative can argue that you get 50% outcome here, you get 50% outcome here. It's possible that here, when multiple photons are coming in, half of them are horizontally polarized and half of them are vertically polarized. ये भी तो possible है. तो ये कह दे उठ के कि half of the photons that come here are horizontal and half of them are vertical, and that is not the same as this. You know that?
सर ऑपरेशन सेम नहीं करते. ऑपरेशन का हमारा वो
नहीं, ऑपरेशन तो वही है. वो अगर horizontally polarized है, वो इस चैनल में भेज रहा है, vertically polarized है, इस चैनल में भेज रहा है.
सुनो ना, हमने ऑपरेशन जो डिफाइन किया था, एस की एक स्पेसिफिक होगी और वही होगी. ऐसे हमने कहा था कि स्पेसिफिक एक वो है पोलराइजेशन,
ठीक है, लेकिन आपने मल्टीपल एक्सपेरिमेंट्स करने हैं प्रॉफिट बिल्डअप करने के लिए, तो आप कोई कंजर्वेटिव आदमी ये कह सकता है कि भाई अगर ये 50-50 पोलराइजेशन आ रही तो आप एक प्योर स्टेट भेज ही नहीं रहे। आप कह रहे हैं कि half of the time the incoming photon is horizontally polarized and half of the time the incoming state is vertically polarized, and that is totally different from this state. This is just multiple photons, each photon has the same quantum state, so this is called a pure quantum state.
So how would the representation of the two photons in the other case would be different from this? Representation same है या उसकी भी?
देख लेते हैं, पहले इस बात को हम खत्म करते हैं कि तीन पॉसिबिलिटीज है। एक पॉसिबिलिटी ये है कि दिस इनपुट स्टेट यील्ड्स दीस आउटकम्स, ठीक है। सेकंड पॉसिबिलिटी, वन हैज दिस सुपरपोजिशन स्टेट, द रिप्रेजेंटेशन ऑफ दिस क्वांटम स्टेट आप बता सकते हैं क्या होगी, इज 1/2 1 1 1 1, still it's a ket, it's a vector, it's a superposition, this is also a superposition. Both of them give the same outcomes with respect to this experiment only. The third possibility, one might argue, is that the signal or the either photons, they are not coherent superpositions, rather they are mixtures. And how do we represent such mixtures? That's a different question. We cannot represent them by kets. Okay? There's a different way of representing these states, which are mixtures. तो मैंने लफ्ज़ यूज किया है mixtures का, इसको हम तफसील से देखेंगे। We cannot represent them by kets, rather we represent them by density operators, ठीक है। So these are pure quantum states. So there are two possibilities of pure states that yield the outcome that we've seen here for this particular experiment, and there is also the possibility of having a mixture, ठीक है। अब देखिए, अब हम एक और एक्सपेरिमेंट परफॉर्म करते हैं। PAHB. This is an analyzer along the HB basis. Another analyzer along the HB basis. Okay. Two possible outcomes: +1 -1 of HB HB. Now we're looking at both of these outcomes simultaneously. Okay. We're not rejecting any photon. So now what is the probability? Now we have to talk about joint probabilities. What's the probability that H appears on the first photon? The first photon is horizontally polarized and the second is horizontally polarized. Okay? बादी नजर में या ज़ाहिरी आंख से तो लगता है कि अगर इन दो एक्सपेरिमेंट्स को देखें ना, the probability that the first photon is horizontally polarized and the second photon is also horizontally polarized, what's the problem? What does it apparently look like? 1/4, 0.25, because there is a 50% probability of observing horizontally polarized photon here and 50% probability of observing horizontally polarized photon here. H देखने की probability 1/4 है, HB देखने की probability 1/4 है, BH की 1/4 है, BB की 1/4 है, because these are totally random events and they are independent, they have nothing to do with one another. Okay, but lo and behold, what happens is that this probability of observing H on the first photon, given that you observe H on the second photon, probability H bar H. Okay, I'm not talking about probability of H and H. If the second photon appears to be horizontally polarized, if it is projected on the horizontal state, then the probability of seeing the first photon in the horizontal state is equal to 1. Remember, this is not probability of H and H. It's a probability, conditional probability, that if the second photon appears is if this detector fires with the second photon, then always it's going to happen. Always it's going to happen that this detector is going to fire. It becomes totally non-random. That if the horizontally polarized photon fires here, then the horizontally polarized channel fires here in 100% of the cases. We can prove that mathematically, but this is something totally counterintuitive. You just look at this, it appears to be totally random. You just look at this, it appears to be totally random. But when you look at both the outcomes together, if the horizontal channel fires here, then with 100% certainty the horizontal channel will fire.
So is it because the instrument is built in this way?
No, it's not nothing to do with the instrument. It just is inbuilt into the state.
कार्टेशियन सिस्टम में एक में या तो हॉरिजॉन्टल आ रहा है या वर्टिकल आ रहा है, इसलिए दोनों के पास
ओके अगर ऐसे हो क्या मतलब
एज एन सिस्टम में आफ्टर द क्रिस्टल सिर्फ एक हॉरिजॉन्टल फोटोन आ रहा है या फिर एक वर्टिकल फोटोन आ रहा है,
यानी ये दोनों तरफ हॉरिजॉन्टल है दोनों तरफ वर्टिकल। हां चलो देखते हैं अगर एक प्रोबेबिलिटी दैट दिस given the second photon is in the state is vertically polarized, then this is also equal to 1. Okay? The probability that the second photon turns out to be horizontal and the first photon appears to be vertical is 0. And the probability that the second photon is horizontally first photon is horizontally polarized given the first is vertical is also 0. So these are the 4 outcomes that you observe. Now we have a totally confounding result here. On their own, the two channels seem to be totally random. But if we look at the measurement outcomes, both of them simultaneously, there is perfect correlation between the outcome here and an outcome here. Now let me give you a simple example and then I will also answer it. Suppose I have 2 points. Okay, one point head or tail with 50% probability and another point head or tail with a 50% probability. Now both, if I just look at this point, I'll get heads with 50% probability, tails with 50%. This is also totally random. Okay, when I look at them on their own. But suppose I entangle the 2 points. Okay, I entangle the 2 points. I create a state which goes like head plus tail. Suppose I create this superposition state. Okay?
So you are entangling 2 coins here या एक दो sides को entangle किया ऐसे ही क्या किया?
पहले मेरी बात समझ दो कि देखो ये हमें सुपरपोजिशन स्टेट की 2 पॉइंट्स के दरमियान 2 पार्टिकल्स के दरमियान ठीक है, एक मैं लेके अपनी जेब में बैठ जाता हूँ, दूसरा मैं भेज देता हूँ मरीज को। ठीक है, अब मैं अपने पॉइंट को देखता रहूंगा ना सिर्फ, और वो सोया होगा मेरा भाई आप के कोच में, मैं अपने पॉइंट को टॉस करता रहूंगा, मुझे कभी हेड मिलेगा तो कभी टेल मिलेगा। ठीक है, लेकिन मेरा भाई जागता है और वो भी अपने पॉइंट को देखना शुरू करता है और हम एक ही वक्त में मेजरमेंट, मैं एक मेजरमेंट में पॉइंट टॉस करता हूँ, मुझे हेड आता है, वो भी पॉइंट टॉस करता है, हेड आता है, उसका भी हेड आएगा, हम दोनों फोन पर पूछेंगे यार तुम्हारा क्या है, कम्युनिकेट करोगे मेरा भी हेड है, मेरा भी हेड। ठीक है, चलो एक और इंटैंगल पेयर लेते हैं, अब वो स्टेट डिस्ट्रॉय हो गई। ठीक है, अब मैं एक और इंटैंगल पेयर लेता हूँ, बिल्कुल इसी तरह आइडेंटिकली प्रिपेयर्ड। ठीक है, इवन दो आई कांट क्लोन क्वांटम स्टेट बट आइडेंटिकली प्रिपेयर्ड कॉइन लेता हूँ। ठीक है, मैं आप टॉस करता हूँ, मेरे इत्तेफाक से टेल आ जाता है, मैं सोचता हूँ तुम्हारा क्या आउटकम आया, मेरा भी टेल। अगर मैं उसके आउटकम ना देखूं और अपने पॉइंट्स को फेंकता जाऊं इंटैंगल पेयर में से एक पॉइंट को देखते हूं, मुझे एक टोटली रैंडम स्ट्रिंग नजर आ रही है। तो आई गेट स्ट्रिंग ऑफ हेड हेड टेल 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 हेड टेल हेड टेल 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 सो ऑन। लेकिन जो मेरा भाई है उसको मरीज पे यही स्ट्रिंग नजर आ रही है, as if my action of making a measurement is somehow we communicated superluminally at speeds higher than the speed of light, somehow that the system readjusts itself to get the same outcome. So this is the entanglement, this is the hallmark of entanglement. such an input state, this Bell state is an example of an entangled state. And it appears that we have parts in a system, the parts are random, but the composite system is less random. The composite system is totally deterministic and the outcomes are perfectly correlated. So the sum is less random than its parts. The parts are random, but the sum is not random. Okay? Now we have to describe all of this quantum mechanically using the probability theory. And this is something we will do in the next class. And I will also introduce this concept of a density operator. How do we describe mixed states? This is a really important concept and really ill understood. Okay? Sir,
is it because we're entangling head with head, which is why we get this correlation? If we entangle head with tails, then we would always get, if one person gets head, then the other person.
Yeah, you can have anti-correlation. You can have, there are 4 kinds of Bell states.
How, sir, do we entangle them in the physical way?
This type 2 down to measure process is physically entangling the states.
How do we achieve that?
Shine light on a crystal, on a particular crystal and a particular orientation, the output is perfectly entangled. There are different ways of creating entanglement. That come with more examples. Okay. Suppose let me finish up by stating the 4 Bell states. We have 5 plus is 1 over under 2 H plus B. Okay. मैं टेंसर का साइन बार-बार नहीं लिखता हूँ, ठीक है? The other is 5 minus. 5 minus has a minus here. Okay. I can also have 2 more Bell states, which are represented by psi plus minus 1 over under 2 H V plus minus V H. So these are the 4 Bell states, and they also form a basis for the 4-dimensional Hilbert case. Right? For the 4-dimensional basis, we can have an infinite choice of basis states. So these states also form a basis, and you can prove them by noting that phi plus, phi minus, they are orthogonal, right? Psi plus, psi minus. All of them are orthogonal. Okay. These are 4 basis vectors that are mutually, they are orthogonal, so they must form a basis. Okay, so the 4 Bell states also form a basis of the 4-dimensional space. Okay. Now we use the concept of density operator to describe what's going on, how do we calculate these probabilities. We'll talk about the reduced density operator, and this is the beginning of the field of quantum information theory, quantum computing. It all starts from it, and this is a future that you cannot observe classically. Okay, you cannot observe this future classically. So this is the hallmark of quantum mechanics. Superposition is hallmark of quantum mechanics. Entanglement, non-locality, and realism. These are the 4 or 5 hallmarks of quantum mechanics, and all 3 of them are not dealt with in undergraduate courses. We just talk about superpositions. It's something very strange. Okay, but I'll spend some time on these concepts. Okay, and so I will discuss these concepts, and one important area that is left open in this course is how do we add angular momentums. So you have 2 electrons with different spins. What's the total angular momentum? You have an electron that has an orbital angular momentum and a spin. What's the joint? What's the new angular momentum? So how do we add angular momentum? This is something that's left over in this course. Okay, and so we'll keep on talking about quantum information, entanglement, multi-particle quantum mechanics, non-locality, realism. We'll then go on to adding angular momentums, and probably we'll finish off with, I will use the concept of quantum field theory. Some basics. Okay. Alright, thank you very much.